Hello and welcome to our presentation. Our project is titled Large Angle Flexure for Oscillating Heat Pipes in Space. This is done through the Department of Mechanical Engineering at Cal State LA. Our senior design members are me, Spencer Miesner, and my partners are Anthony De Leon, Sufi Asadi, Allan Hernandez, and Christopher Molina. Our advisor for this project was Dr. Jim Kuo through Cal State LA. Our liaison was Dr. Scott Roberts at JPL, and our partner for this project is NASA Jet Propulsions Laboratory. The agenda for our presentation is, first we'll start with the introduction. We'll give a background to our project, a summary of the problem, our objective for the project, and our minimum requirements table for our designs. Then we'll do a design showcase where everyone in the group will go over their individual designs. We'll do a testing overview where we talk about how we 3D printed flexures, and then we'll also talk about our experimental procedure and our simulation procedure. Finally, we'll do a trade study in which we select a winning design between the group's designs. We'll do a final evaluation of that design and see how it matches with the minimum requirements. And then we'll talk about what's next for large angle flexures. So to give some background on our project is a part of an effort to develop and improve CubeSats. CubeSats, which are short for cube satellites, are miniature satellites that are used for space research. One thing with CubeSats is that their internal components generate heat, and this heat can be detrimental to the performance of the CubeSat. The way we get around that is by cooling, and through that we do cooling in space or in orbit by radiating heat into space. That brings us to the summary of the problem. The current cooling technologies used in CubeSats limit how much power can be used in the CubeSat, as more power generates more heat. CubeSats have a limited surface area, and that surface area is needed to radiate heat into space. So what some CubeSats do is they use deployable radiators to increase the surface area of the CubeSat. Issues with this, however, are that there's difficulty in transferring heat across those mechanical hinges that allow the radiators to deploy. And you can see in the two bottom pictures, those are examples of some of the mechanical hinges that are used on CubeSats. The issues with these are that they have low contact, so trying to conduct heat across them isn't ideal. One way to get around this would be to use heat pipes, which transfer heat via fluid flow. For this CubeSat design, we'd like to implement an oscillating heat pipe system. And what an oscillating heat pipe system is a two-phase flow device. It uses oscillatory motion to transfer heat from an evaporator to a condenser. This is a very effective method of cooling and has high thermal conductivity, but would require flexible joints to be able to have deployable radiators. That brings us to our objective for this project. How can we create a flexure that can bend to allow the radiator to be in a stowed position, allow fluid to flow through to accommodate that OHP system, and as well be 3D printed? And you can see images on the right of how this worked in an open position as well as a stowed position.
So as you can see on this slide, the project had minimum requirements in order for the project to be deemed successful. As you can see on this slide, there's a table that shows each requirement from flexibility, strength, coil length, uncoil length, width, height, mass, and manufacturability. As to the right of it, there is a brief description of what each of this requirement has. As you can see, flexibility, it is an important requirement because we need our hinges to be flexible in order for them to successfully bend and to put the radiator in a stowed position. The strength is also an important requirement because we must have a factor of safety of at least 2. The other requirements are important, as you can see, like coil length, which would have a maximum length of 8 centimeters, and width, height, mass, and the manufacturability being another important requirement because we need to 3D print the flexures in order to get experimental data to validate our simulations.
So to start with our design showcase, we'll start with my design, which is the serpentine structure. The reason I decided to do a serpentine type structure is because of its already usage as flexures. One of the places it's commonly seen and used in is MEMS, which is known as, which is short for micro electromechanical structures. Um, Additionally, with these designs, there's a lot of freedom of design, and you can see from the different iterations of designs that I've done, there's a lot of different changes and things that you can do with these designs to try and maximize its ability to bend and fulfill the other requirements. Additionally, there's lots of room for optimization. Because there's so many different dimensions, you can change and adjust all these different dimensions to try and make the best flexure as possible. And that's what I've done this semester with this serpentine structure. And you can see the final design I came up with at the top right.
The next design is a circle with an inner ellipse. The main reason why I chose to use an ellipse as an inner shape is because comparing an ellipse to a circle, ellipse has lower area, which can result in thicker walls for our design. And in this specific design, because deflection and handling the stress is one of the most important factors that we look into, I decided to make the walls thicker so it can handle the stress better. However, with that being said, smaller area means a smaller room for the liquid to flow. So there's definitely some validation that needs to be done in that area. Starting from the left design, I started with a lot of area in between each segments, and then after running some simulations, I realized that the angle of deflection is really well, but when it comes to handling the stress due to the weight and the actual overall design pack, you may not be able to handle a lot of stress. So I decided to the second design, which is going to be in the middle of the screen. And after adding more segments and making the uncoil length a bit larger, I started getting better results. And after updating the design and just increasing the factors, I got to my last design, which meets the criteria that we had and we agreed on. And at the end, the main three reasons why I decided to go with this design is first, because of a thicker wallness, thicker walls that can handle stress better, and more angle increases in the deflection, and the circle has the most angles for the outer shape. So we started with triangle and then we moved to square and so on. And as we added more angles, we started seeing better results. And obviously I chose to go with a circle because that almost has most amount of angles when it comes to there. And then at the end, the last reason is the most amount of engaging due to not having sharp edges. When we tried some square and some sharp edges in our design, we did see that the almost the edge of the design is not engaging a lot and it's not handling a lot of the stress. So we could easily cut down material in that case by just changing the design to circle. And I'll pass it to the next design.
Thank you, Sufi. So this is my hexagon spring that I worked on throughout the year. The inspiration came from the honeycomb uh, compactment that is done by bees in their honeycombs. I just thought it would be interesting to explore this idea within our flexure. Um, the findings that occurred from the testing and the simulations were that as the number of turns increased, the flexibility also increased, meaning that a spring with a higher number of turns would bend at higher loads compared to. So a higher number of turns meant the spring was able to bend more at the same loads and was able to sustain higher loads. The maximum stress was always found near the fixed end uh, at a corner as shown by the red arrow on the slide. Failure usually occurred at the location of the maximum stress, as seen once again by the red arrow. Um, the failure occurred on at the experiment level, where various springs were tested, various pitch springs, and they all failed at at a similar location. The improvements made throughout the year for this spring were modifying the number of turns. Overall, this meant increasing the pitch because of printing restrictions. My initial design, which had 20 turns, was not able to be printed, so the pitch had to be increased, resulting in fewer turns of the spring. And because of the hexagonal shape of the spring and the wire, they both had to be filleted, which resulted in a decrease of the stresses. But overall, the design was kind of limited because of the hexagonal shape. The hexagonal shape would result in higher stresses, but it was studied just as another design. Now I'm passing it on to Chris.
For my design, I decided to go with the reverse hourglass spring. The reasoning behind my design is because of its similarity to a normal helical compression spring. Since the graduate students that are working along with us are studying a normal helical spring, I decided that a small geometric difference at the center of the spring would allow for a comparison of the performance to see how changing the height at the center of the spring would show differences in its performance. Also, by changing the center height of the spring, it's hopeful that it will diminish the stress at the edges, which is connected to the CubeSat, at the cost of its own flexibility. As seen from my previous designs, from my first to second iteration, the increase in the length of the edges would allow for more flexibility to occur, but the drawback is that the slope in which the height at the center of the spring is increasing was too drastic. Therefore, for the final design, the slope at the center of the spring was decreased so that the change occurring within the center of the spring would be marginal.
So, with my design, it was basically the idea was inspired by the graduate students, since they're working on helical compression springs. Um, I decided that I wanted to do something different to see how stress and deflection occurred with the flexure. Uh, Originally, as you can see on the top left, the previous design uh, was very small, and pretty much I had really no idea of how it was going to function or if it was even going to simulate in SolidWorks. But it turned out to be that it was a successful simulation. So my goal uh, pretty much was to optimize the first design, and then as you can see, there's different iterations of the designs. Towards the end, the final design, uh, the reason why this optimization step occurred in this design is due to the fact that when JPL tried to 3D print one of my flexures, there wasn't enough spacing in between each turn. So what I ended up doing was, although the total number of turns was reduced in the design, I was able to create more space between each turn, and thus ended with the final design. Uh, but yes, that's basically my thought process of what happened. Uh, I ended up simulating one spring, and then we just, like all of us, we just went through different optimization process, different iterations of optimization, and ended up with the final product that can be manufacturable and can meet the minimum requirements which were stated in the minimum requirement table.
For our project, we had two different types of methods for testing our springs. Our first method included experimentally testing our 3D printed PLA flexures, while our second method included our FEA analysis of in both SolidWorks and ANSYS. The purpose of testing our PLA flexures is so that we can use our scaled PLA experimental data and validate the same PLA scaled flexures in FEA against each other so that when we do our aluminum FEA simulations, we can better describe the flexure without requiring experimental data. An overview of our 3D printing our flexures includes a final goal where our final flexure would be printed in metal via powder bed fusion. Unfortunately, we couldn't have access to the 3D metal printer at JPL, so we had to think outside the box. Flexures for experimental testing were done at home via PLA 3D printers. The small challenges that occurred with printing in PLA included flexures with detail and little to no imperfections, since the flexures themselves had to have a very rigid foundation and strong support structure to be printed at all in the first place. As you can see in the images to the right, the images on top is a representation of what our springs or flexures would look like printed in metal, whereas our springs printed in PLA is the image below. For our experimental procedure, our goal was to measure the deflection at the edge of the flexure via test weights that are seen in the image below. The flexure was clamped at the boss head clamp on the rigid rod, and a tripod was set up with a phone to take pictures so that the deflection can be calculated after each test weight was applied and removed.
So one of the ways to validate our requirements table was to use a simulation process or a simulation procedure. The simulation procedure would then be compared to the experimental data, which we would receive from the experimental setup that was shown in this presentation. The simulation process was done through ANSYS or SolidWorks. Mesh sensitivity tests were used to determine the mesh sizing needed to give us accurate simulations. The process basically was we made one end of the flexure a fixed end, and then the opposite side, which would be on the other side of the flexure, to apply a force which would bend our flexure. The large deflection setting was used on ANSYS, and in order to observe how the flexures behaved, forces were applied in different increments from zero point 0.5 newtons to 5 newtons. Based off of the simulations, aside from the displacement that was recorded, there was also an important data that needed to be recorded as well, which was the von Mises stress. Uh, Both the von Mises stress and the angle of deflection are the most important requirements for our flexure and for our project. If we don't understand how the flexure behaves, then the project will essentially fail. So it is important to understand how the flexure behaves under a force and how the stresses act on the flexure. As you can see, a quick glance of how the stresses works in this simulation is that most of the stresses will be at the fixed end. And that's one important observation that can be seen from the simulation. And that was the purpose of simulations, to understand the behavior of our flexures.
We have conducted a trade study in parallel with our graduate students, and we finalized multiple categories to go ahead and rate each design, including our graduate student designs. We did have a longer list for our categories, but due to not being able to correctly measure every single one, we cut down the list to the list that you can see all the way on the left-hand side. We also rated the importance for each specific category so we could best suit the design and choose the winning design that we had. Starting with the flexibility, we had that at 19% importance, and then we rated anywhere between 1 to 3, 1 being the lowest and 3 being the highest. We also rated strength at being one of the highest, just like the flexibility at 19%, because those are the two main categories that we were looking at. We also had some design constraint, and due to that, we had to also look into the coil length, and that's something that we were able to make adjustments on. We also looked at the uncoil length as well because at the end that's also part of the system design requirements that we had. And when it comes to the width and mass, we rated those next at 10%. And then we also looked into the manufacturability of the design. When it comes to designs that are getting small, it may be hard for certain designs to be printed, especially because of the post-processing um, factor that needs to be accounted for the design. We also wanted to look into that factor as well. And then after we went through a specific rating in our designs, the race was between the Serpentine design and the reverse hourglass spring, which the Serpentine was able to make the highest amount of the points out of the all, and that would be as a winning design. Moving on, for the final design evaluation, we broke down those specific categories that we talked about in our trade study, and then we um, went ahead and compared that to our final design evaluation. So for flexibility, we wanted to be able to deploy the radiator with the stowed position, and the winning design was able to flex up to 24.19 degrees, which is not enough for fully bent when it comes to that design. And moving forward, for the strength, we have a factor of safety for at least 2, and the factor of safety that we had on the design was 0.27 for full bend and 0.54 for the half bay bend. We also looked at the coiled length, which we had a maximum of 8, and we were able to pack it in a 6 centimeter design, which is lower than expected, and that's actually a positive thing when it comes to the design. And when it comes to the uncoiled length, we want it to be efficient in order for it to be fitting in the specific volumetric space that they had on the CubeSat, and we were able to fit everything in 100 millimeter, which is mainly low. When it comes to the width and the height, the specification was to have a maximum of 8 millimeter, and for both width and height, we were able to fit it into 8 millimeter. When it comes to the mass itself, the mass was the maximum of 2.5 grams for the specific requirements that we had, and the winning design had a 1.14 gram, which is great. And when it comes to manufacturability, because it is the design will be 3D printed in the metal through the power bed fusion technology, we were able to have the client print some 3D models, and after the post-processing, they were able to make the design printable with some small adjustments. And then moving on.
So what's next for large angle flexures? Well, we already simulated and did experimental experiments on PLA flexures. So the next step would be to test metal printed flexures to further validate the results that we got. We didn't do too much testing with metal printed flexures, but that would be the next step. We want to validate and see the same results that we saw with PLA printed flexures. Aside from that, we also want to further optimize our flexure designs to increase the factor of safety. The factor of safety, as mentioned, is one of the big requirements in our project. We want to meet the factor of safety of 2 or below that number. Furthermore, as you can see on the right hand side of the slide, we want to design a support structure that will allow our flexure to sustain larger forces and essentially bend the total amount of degrees that we want we want our flexure to bend in a particular way, and by adding a support structure, we not only accomplish that by allowing the flexure to bend in the way that we wanted, but we also reduce the stress. Uh, from the results, we saw that at the fixed end was where all the stress was located at. With a support structure, that alleviates the stress that is felt by the flexure at the fixed end, and it spreads out the stress throughout the flexure so that it isn't felt at the fixed end. That will be the next step in this project and for the CubeSat. And that's it. Thank you guys, and that's our presentation.